Welcome back, everyone. Thank you very much for viewing our YouTube video. In this video on CAPS Mathematics Grade 12, we will focus on the topic Euclidean geometry. This is a two-part video series. In part 1, we're going to look at the proportionality theorem and converse, and in part 2, in another video, we will look at the similarity theorem and converse and all the applications. I hope you will enjoy the video. In this video on Euclidean geometry, which is part 1 of 2, we'll be focusing on the grade 12 topic, which is proportionality of triangles, the proportionality theorem. I'm going to show you how to prove the theorem, how to approach problems relating to proportionality, and the converse of the proportionality theorem as well. Hope you will enjoy the video. This video consists of 4 sections. First of all, we're going to look at the proportionality theorem as well as the converse of the proportionality theorem. Then we're going to do some applications, direct applications, and then which will be followed by area calculations relating to the proportionality. And then, as usual in all my videos, there's an exercise worksheet. In this first unit, we're going to introduce you to the proportionality theorem. We're going to show you the formal proof of the proportionality theorem, as well as the converse of the proportionality theorem, with some direct applications to assist you with the use of the proportionality theorem. Let's look at the statement of the theorem. A line drawn parallel to one side of a triangle. So there we have a triangle. And we have a line DE, which is drawn parallel to BC. That's the given information. Then this line DE will then divide the other two sides. See, there's the other two sides, AB and AC. It will divide it proportionally. What do we mean by that? It is AD over DB will be the same as AE over EC, right? We could also state it as follows. If we take a triangle ABC, and there we see the line DE is parallel to BC, let's do exactly the same. We can have AD over AB, and we can have AE over AC, which is exactly the same as DE over the shorter parallel side over the longer parallel side. And this is the theorem of proportionality. If you have a line drawn from one side to the other side, and that line is parallel to a third side, right? Then this line here divides the other two sides proportionally, as we indicated here. AD over DB is the same as AE over EC. Or we can even take AD over the total length AB, or we can take AE over the total length AC, and that will be the same as the shorter parallel side over the longer parallel side. In this slide here, we're going to do the formal proof of the proportionality theorem. To be able to do this, we're going to use triangle PQR with S a point on PQ and T a point on PR, such that ST is parallel to QR. And we want to prove the theorem, which will state that PS over SQ is PT over TR, right? So we want to prove the proportionality, that this ST divides the other two sides in proportion. Now, the proof of this theorem is examinable for grade 12 in CAPS, okay? Now, to be able to do this, we need a construction to assist us with the proof. So our construction is we draw SR and we join QT, right? Now, we also need to put in the height H1, right? And we can see this H1 is the height of triangle PST, and it's the same time the height of triangle PQT, right? And it's the same time the height of triangle QST. Similarly, we put the height in for the other. This is the height of PST and ST R. Now, this proof here requires the use of the area rule of triangle. So the area, when you take triangle of PST, so there we take triangle of the PST over the area of QST, the white and the blue triangle. Area of a triangle is half base, so the PST's base is, that's correct, is PS, and the base of the QST is SQ. You can see the halves and the half cancel, and they have the same height. So the heights can also cancel, and that leaves us with PS over SQ. Okay. And the reason why we could cancel the heights, because they're the same heights. You see, T is the vertex there for this base PS, and it's also the vertex there for this base SQ there. So it has the same height. Similarly, we can take PST. Let's take that away. And we take it now with STR, right? So let's take that portion away, let's take that height away, and let's put in the height that applies to both of them. The same way we can take the area of a triangle. So in this case, it's half, the base is PT and the height is H1. For this magenta one, the base is TR and the height is also H2. The halves can cancel, the H2s can cancel, and that leaves me with PT over TR. And why we cancel the heights? Because they're the same. Now, if we look at, you see in both cases there we had PST and PST, so it's the same PST, so they are common. Right? We're just comparing these fractions there. That numerator and that numerator is the same. Let's compare the denominator part. QST. Let's look at QST. There's triangle QST. It's hidden behind that magenta one. Right? Let's take those things away, so we can just look at the QST and the STR. Now, what do we know about them? That's correct. They both have a base ST, and they have the same height because they lie between parallel lines. So let's write that down. QST is equal to STR. Why? Because they have the same base ST, and they have the same height because they lie between the same parallel lines. Now, if you can see what we've done now, we compared the numerator and the numerator and the denominator and the denominator. So this fraction is equal to that fraction. So let's just write that down. But the first fraction there, we simplified it as PS over SQ. And the second one we simplified as PT over TR. And there we have done our proof there. You can see PS over SQ is PT over TR. And this is the proof of the theorem of proportionality. And as I mentioned, it's examinable. It's important that you go through this, but understand it, don't just memorize it there. Now let us consider the converse of the proportionality theorem. Okay. We have a triangle PQR with point S and T respectively on sides PQ and PR, right? Such that PS over SQ is equal to PT over TR. In other words, we are given the proportion. Then, if those sides are in proportion, then ST will be parallel to QR. Now, this converse of the proportionality theorem is not examinable, so I'm not going to show you the formal proof. Let's just try to understand the converse, and we can do it this way. So if I take PS over SQ, in other words, PS over SQ, it's exactly the same as PT over TR. Right? So if I have PS over SQ and it's the same as PT over TR, this would imply to me then that that line ST will be parallel to QR. So if you have the proportion, it implies the line will be parallel. If the line there is parallel from the original, if it's parallel, then the sides will be in proportion. If the sides are in proportion, the line would be parallel. And this is the converse there. Formally, we can state the converse theorem as follows. if a line divides two sides in the same proportion, so the line, there's the two sides, divides it in the same proportion, right? So the ratio I get on this side is the same as the equal to the ratio on the right hand side. Then that line will be parallel to the third side. Remember, triangle is three sides, these two sides, and that's the third side. And this is the converse of the proportionality theorem, right? You need to be able to apply it, and we'll show you how to apply it. Now, in the next few slides, we're going to just do a direct application to see how you can write down the proportionality from given diagrams. Let's take the first example. So there we have a few, and I'd like you to try that on your own. So let's see, that's PM over MQ. Let's follow that. PM over MQ is the same as PN over NR. Let's see whether you follow this one as well. MN over QR, what will that be equal to? That's correct, it will be PM. Now I have to take PM over the total length PQ, or I can take PN over the total length PR. Okay, let's take a second example. Complete that, and you are given a chance to try it on your own, right? 1 minute, and then you come back. Let's look at the solution. There we have ds. We're starting here. ds over, that's right, you can take ds over se. But if I take ds over se, I must take it in the same order, fr over re. fr over re. SR, that's the parallel line. And you always associate this shorter one with a longer one, which is DF. Now, this will be ES over ED. I could also write it as what? That's correct. Also, ER over EF. Right? You also need to practice triangles. The triangles won't always be in the form it was proved in the theorem. Sometimes the triangles can have the parallel lines either horizontally, or you can see the parallel lines is going here at an angle here. Now let's take another example here. Let's look at the diagram. You can see there I've got three parallel, BE parallel to CF and CF parallel to DH, right? So I've got more than one pair of parallel lines. Now there are 4 proportions that you need to complete. Pause the video, try them, and then after that let's resume and see whether you've got the answers correct. Come, let's look at this now. AB, so that's AB. So I can take AB over BC, right? And then the same time I can take AE with over EF. Let's look at AC. There's AC. I'm using this pair here. So I can take AC over CD. And then I need to take AF over FH. Let's look at the next one. BE is a parallel line. It can go with CF. So it's BE over CF. And then I now need to take AE over AF, right? You see there you've got a shorter over a longer. So you need a shorter over a longer side there. Let's look at the next one. There I've got CF. There's a parallel line. I can take CF over DH, right? So I've got the short over the long one. So CF, and I can take it on this side here. AC, that's the shorter over the longer side, it is AT. Let's look at another example. As you can see, I've got 2 pairs of parallel lines. Now, it's recommended that you rather, highlight the one pair and the other pair. It's much easier to focus on what you're doing there. Now, here we have 4 proportions that need to be completed. Pause the video and try to complete it on your own, and then you'll see there. Okay, let's look at your solutions there. But before we actually look at it, just see how the colors can help us. EB. So I know it's with the yellow, so I have to focus on the yellow pair. So it will be EB, and I need another yellow. It will be over BD. That's the first thing I do. Okay. Now on the other side, I need the yellow again. So that will be EA over AC. Right? Let's look at the next one. AB. AB is the parallel line. So I need to focus on the other parallel line. So it will be EB over CD, right? Then that will be EA over EC. Okay. Now let's look at the DF. DF is the purple parallel line, so I need that parallel with that one, so it will be HA over DF, right? So it's HA over DF and EA then with, now I'm going to need to go to the purple, so it's EA over EF, right? Let's look at the last one. I have EH, so there's the EH. And then I've got EF, so I'm taking the whole one. So it will be EH with ED. I must take the whole one there. And then it will be EA over EF, right? Can you see by highlighting it, it can assist you. Because if I take EB, you can see now I have to focus on the yellow. I need to focus on that pair, right? There I have EH, so I have to focus on the purple pair there again. Now I'm going to look at one example where we can apply the converse or the proportionality theorem. There we have a diagram with triangle ADH, and P, B and E are points, and C and F are points, and the length AB is 60. So we are given various lengths there, all the measurements there. Now we are required to determine which lines are parallel to each other, right? So we can use the converse of the proportionality theorem. Now you are given a chance there. Let's give you 3 minutes, or now 4 minutes, to determine which lines are parallel to each other. Is BE parallel to CF, or is CF parallel to DH, or is BE parallel to DH? We'll just give you a chance there. 4 minutes should be more than enough. So let's try this. AB over BC. AB over BC, let's substitute the length, that is 60 over 45, and we simplify that, that's 4 over 3. We'll also take AE now with EF. AE with EF, that is 90 over 70, and we simplify that, 9 over 7. We see that 4 over 3 is not equal to 9 over 3, right? So there's no proportion there. Therefore, AB over BC is not equal to AE over EF. And because they're not equal, BE is not parallel to CF, right? Let's look at the other option. If I take AB now with the BD, AB with BD, AB is 60 and BD, if you add that up, it is 80. And that gives me 3 over 4. So let's try the same. I took AB, so I need AE with EH. AE with EH. AE is 90 and EH, if I add that up, that gives me 120. And if we simplify that, so we see that AB over BD is exactly the same as AE over EH, right? So they are in proportion, and if they are in proportion, it means that the BE will be parallel to the DH, right? You can actually see that. You see there's an A and an A. You take the A and A left, you're left with BE. You take there, I've got BD and EH. Okay, and this gives me a DH there. So BE is parallel to DH. So this BE is parallel to DH. Because BE wasn't parallel to CF, it also means that CF won't be parallel to DH. Now, next we're going to look at some applications of the proportionality theorem, right? So there we've got our proportionality theorem, and whenever we see this, pause and try, stop, do the solution your own, and then you continue again, right? But always make an attempt to try it on your own first, and then you compare the solution. So whenever this pops up there, pause it and you try it on your own, and then you restart again. Let's look at our first example. Here we actually have a real-life application to the proportionality theorem, right? In the diagram there we have a street map, and we've got Mandela Drive. So let's see, where's Mandela? There's Mandela Drive, and we say Mandela Drive is parallel to New Street. There's New Street. Okay, so in other words, DE is parallel to BC. AD is to DB. AD is to DB, that is going to be 2 parts, and that is 3 parts. AB is, so the whole AB's length is 2 kilometers. AE is 900, let's just follow that, so that's 900 meters, and DE, this little portion here in New Street, is 600 meters, and there's some lengths that we have to determine. Okay, so in the next slide we're going to actually do this, complete the solution, but you can see there a very simple application that we have there. Let's look at our given information there. We have DE parallel to BC, and there we've got A is 900, ED is 600 meters, and AB is 2 kilometers, and AD is to DB is 2:3, so we write 2x is to 3x. We're going to calculate AD. So AD there will be 2 parts, and DB is 3, so AD is 2/5 of the AB. And 2/5 of 2000 meters is 800 meters. Now to calculate DB, we just subtract 2000 minus 800 gives me 1200. Next, we want to find EC. EC, there we can use the proportion. DE is parallel to BC. So AE over EC is equal to AD over DB. We substitute. That gives us 900 over EC. It's 2/3. We can cross multiply and we can calculate EC, which is 1350. Let's look at the third question. BC. To find BC, that's a parallel line, so we need the DE over the BC and AD over AB. We substitute 600 over BC and 2 over 5. Therefore 2BC is 5 times 600, and BC therefore is equal to 1500. Let's look at what we have here. In the diagram we've got 4 terraces that are parallel to each other. Those could be plantation terraces. You can see there's terrace 1, 2, 3 and 4, and they are parallel. So DH is parallel to CF, which is parallel to BA. We've got some measurements. AB is 240 meters, from A to B is 240 meters, BC is 180 meters, AE is 200 meters, and CF is 360 meters, and FH is 300 meters. And we want to calculate these lengths. So let's look at the question here. Got all our information. Let's highlight the parallel lines, and let's look at EF. EF, there's E and F, so we need BE and CF. So we don't need the other parallel line. Just to help us, just cover it up. Now we can have AB over BC and AE over EF. And we can substitute the values. 200 over EF, 240 over 180, and we can cross multiply and calculate EF. Once you calculate it, maybe it's advisable just to insert it there. Now we want AD, so we just, there's AD, and we don't need that there, so we can take AB over AD and AE over, you don't need that other parallel line there. And substitute 240 over AD and 200 over AH is 200 plus 150 plus 300, that's my 650. Again, as usual, cross multiply and calculate AD. DH, so I need the parallel line, but this parallel is unknown, the other one is also unknown, so I need the middle one. Let's cover up the first one, and now I can get my proportion. CF over DH and AF over AH. CF, that is 360, DH is unknown, AF is 350, and AH we worked out previously is 650. Cross multiply and DH is equal to. Now if you end up with a value like that, rather leave it in the exact form. Don't round off unless it's specifically stated that you should round off to a certain number of decimal places. Let's just get our diagram back again. There. Let's look at our example here. Here we have a diagram with PE parallel to CD, and we have PF parallel to CE. So let's say BF parallel to CE, let's put that in green, and the BE parallel to CD, let's put that in yellow. So it's much easier for us to distinguish there. We've got AB is 4 and BC is 5 and AF is 2 and CD is 10. And these are the lengths that we have to calculate, which we'll do in the next slide. Now let's look at what our given information there. We have BF and we want to calculate FE. We've got BF parallel to CE and we've got BE parallel to CD. So we color coded them there just to assist us. FE. Now if we want FE, you can see F is on the green and E is on the green. So I need to use the BF and the CE to work out FE. So AB over BC and AF over FE. See, I'm focusing on the green pair of parallel lines there. We then substitute. That's 4 over 5. AF is 2. So FE we can just simply cross multiply. And then we get EF is equal to 2, 5. It's always good to insert the values that you calculated. You might need it for the next part. Let's look at the second question. AD. If I look at AD, there's AD. That means I'm going to use, I must have used the yellow. So I'll use CD with BE. So I've got AB over AC, and that's AE over AD. Let's substitute. AB is 4 parts, AC is 5 parts, AE is 2 plus 2,5 is 4,5 over AD. Again, simply just cross multiply and we calculate AD. So AD is 81 over 8. Don't round off, just keep it. Then to work out BE, you can see BE is that pair, so that's yellow, so I need to focus on the yellow pair. So BE over CD will be the same as AB over AC. I could also do it on this side, but seeing that I have 2, it's much easier working on this side than working on that side there. So CD is 10, that's given. AB is 4 parts and AC is 4 plus 5, which is 9. I can simplify, cross multiply. 9BE is 40, so BE is 40 over 9. Do not round up, keep it in that form there. That's a recurring number. Let's look at this problem here. We have triangle ADE with BC parallel to ED and AE parallel to GF. AB is to BE. This is 1 part is to 3 parts. AC is 3 units and EF is 6 units and FD is 3 units and CG is X units. And there we have some questions there, right? I've color coded the parallel lines, so that's BC parallel to ED and GF parallel to AE, so it'll be much easier to follow. Now let's look at the first 2 questions. For example, number 4. There we have our diagram. Let's understand it again. We've got BC parallel to ED and we've got GF parallel to AE, and I've color coded them so it's easy. We have these given measurements. EF is 6 and FD is 3, and then we have AC is 3 and CG is, these are all in units, but we were given a ratio AB is to BE. So because the ratio was given, I write down 1K is to 3K. Don't write down 1 and 3. Now let's look at our question. Calculate the length of CD. So if we look at CD, you can see there, C goes with this light blue parallel line, and same with D. So I'm going to use BC and ED as parallel lines using the proportion theorem to calculate that. So I've got AC over CD is AB over BE. We can substitute. AC is 3, CD is the required, AB is 1, and BE is 3 because 1 is to 3. Therefore, C is equal to 9 units. Let's look at the next question. We want to find the numerical value of X. You know, we just worked out CD is 9. So if CD is 9, we can calculate GD. And GD is thus 9 minus X units. Now, If I look at that GD, let's put in the 9 minus x units there. I now have the magenta colored parallel line. There's it there. So I can use dg over GA and dF over FE. Then we can substitute. dg is 9 minus x and GA is x plus 3. And then this is 3 over 6. We can cross multiply, simplify that, and then we can calculate x, and x here is equal to 5. Let's look at our third question. From the previous question there, we had x equal to 5. So therefore, CG is 5. This was 9, so that will be 4. And we want to calculate the length of BC. Now see, BC is a parallel line, and that's the light blue one, so BC will go with ED. So let's set up the proportion. We have BC over ED, and we're taking AB over AE. You could also have taken it on the other side, but this is much simpler looking for it on this side. So BC is unknown, and ED is 6 plus 3, that is 9. AB is 1, and AE is 1 plus 3, which is 4. We can then calculate BC, and BC in this case ends up as 9 over 4 units. Now let's look at our next example here. Here we have triangle ABC with AD parallel to TE, and we've got that as in purple. That's the only parallel line we have there. AT to TC is 2 parts is to 1. AT is 2, there we put 2K is to 1K, not just a 2 and a 1. And BD is 6, so we can definitely enter the 6. DC is 9, we can actually enter the 9 there. And now we will have some questions to answer there. We'll do that on the next slide. Let's just look at the information that's given here. We've got AD parallel to TE, and then there's BD is given as 6, and DC is given as 9. And AT is to TC is 2 is to 1, so I write 2K is to K. And let's see what is the question we want to answer. You must write down, so you should be able to get that quite easily. If it says write down CE is to DE is the same as 1 is to 2. And there we can just write down the answer. 1 over 2. Let's look at our next question. If CD is 2 centimeters, let's put in the 2 centimeters there. We want to calculate the length of TE. FD and TE are the parallel lines, so I can use my parallel lines there. But before we do that, DE, you see I don't have this measurement here. DE, that is 1 is to 2, so DE is 2/3 of the 9. So we work out 2/3 of 9, so that is 6. And if that is 6, 9 subtract 6 gives me 3. And there I've got 1 is to 2. Now I can work out FD over TE is BD over BE. And if we substitute, FD is 2, BD is 6, and BE now is 6 plus 6, which is 12. Cross multiply. 60 is equal to 24, therefore TE is equal to 4. In this unit, we're going to introduce you to calculations relating to ratios of areas of triangles. Let's just briefly look at the area formula for triangles. There are actually two. The very basic one, area of a triangle is half base times height. So let's just look at this here. So if you have any triangle and you know the base length and you know the height, then you can calculate the area of a triangle. Okay, and in our ratios of triangles, areas of triangles, we're going to make sure that the heights are the same. The key there is the height. Then we have another formula for the area of a triangle, a trigonometric one, which is half the product of two sides times sine of the included angle. Let's just look at that diagrammatically. So you see there's an included angle, and that's the product of the two sides. So it's A and B, so it's half the A times the B with the sign of the included. This angle must be included. And if you're going to compare ratios of areas of triangles, the essential requirement will be that the included angles need to be the same, right? So these two formulas that we're going to use. There are other area formulas for triangles as well, but these are the ones that we'll be using. Half base times height, or half product of the two sides times sine of the included angle. Now let's just do some application to ratios of areas of triangles. There we have a triangle ABE, and we have C and D being points on BE, right? With BC 2 units and CD 3 units and DE 5 units. Let's just compare the areas of three triangles there. So area of ABC, let's see, there's ABC, and the base is BC, and the height, there's the height there, right, from A. Then we have triangle ACD, and the base is CD, and the height is from A, the vertex is at A there. An area of ADE, there's ADE, and the base there is DE with being 5 units, and we have a height exactly the same height. So those three angles have different bases, but the heights are the same. So if the heights are the same, we can make use of our standard formula for the area of a triangle, half base times height. So let's calculate each one. But before we do that, just look at the labeling of the triangles. ABC, ACD, ADE. They all have a A. They all have vertex from the height is from A to the base BC, from A to the base CD, from A to the base DE. So let's calculate there. So if BC then would be the base, and the other one's base is going to be CD, and that base is DE. Ratios can be simplified by dividing throughout by the same value. So let's divide each one by half, by half, by half. H has a value, and the values are the same because the heights are the same. So we can divide by H, and that leaves out that BC is to CD is to DE. We can write the numerical values of that down of the base there. It's 2 parts is to 3 parts is to 5 parts. We can now see that if triangles have the same height, right? So if they have the same height, then the ratio of their areas would be equal to the ratio of their corresponding base measurements. Let's look at another case here. So we want to determine the area of triangles. There we have a triangle ABC, and we have another triangle EDC. If I look at ACB, there's ACB, and we look at ECD, there's ECD. First of all, we notice here that they don't have the same height, right? There's no height, the heights are not the same. So I cannot use my standard formula for area of a triangle. But there's something else that's common. Angle C, right? And we can even see there ACB and ECD. The C is common, and C in this case is a common angle. And if it's a common angle, we can use the trigonometric formula for the area of a triangle. So let's start now. I have AC, CB, sine C. You can see there's, so it's AC times CB. Just place the C in the middle. C, it's included. Let's put it in the middle so it's easy. Then AC times CB. And the other one, you can see the C's in the middle will be EC times CD. I don't even have to look at the sketch. EC times CD. Now, ratios can always be simplified by dividing throughout, right, by the same value. So let's divide by half, divide by half. Now angle C is the same, therefore sine C would be equal to sine C. So we can cancel divide by sine C, divide by sine C. So there I end up with a product AC times CB and EC times CD. Let's just quickly find a numerical value for that. AC, if we look at AC, it's 3 plus 9, which is 12, and CB B is 8 plus 6, which is 14. EC is just the 9 and the 6. And if we simplify that, I end up with 28:9. Okay. Now you can see after the cancelling here, there we had the ratio of the areas. It actually just ends up as a ratio of the product of the adjacent sides. So let's just formulate that. If triangles have the same included angle, see they have the same included angle, right? Then the ratio of the areas will be equal to the ratio of the product of the adjacent sides. So then ECD, the adjacent sides are 9 and 6, so I multiply 9 with 6. There the adjacent side is 12 and 14. Now we're going to consider two examples where we're going to calculate ratios of various triangles there. Let's look at our diagram that is provided. We have A, B, C, and F and D are points on BC, and E is a point on AB, such that FE is parallel to AD, and some of these sides have already been calculated. Right? We can see there 1:2 is the same as 3:6, so a lot of measurements have already been calculated. So we're just interested in finding ratios of areas, or want to simplify some area calculations there. So let's see the first one, area of triangle EBC. So I have EBC, let's see where's EBC, there's EBC, right? And I now look at EFD, and you compare them, we see that they have, that's correct, they have the same height. Okay, and if they have the same height, I can just use half BC, because BC is the base of EBC, and FD is the base of EFD, right? Because E is the vertex that I have there, and there's the base BC and the base FD. We can simplify by cancelling out the halves and the heights. So now we only have to substitute BC over FD. BC is 1 plus 2 plus 5, which is 8. And FD is 2, and that gives me 4. Let's look at the ratio of two other triangles in the same diagram. So we want the area of ABC. And let's just see ABC there. So it's the large triangle there, ABC. And we want to find EBC. Let's look at EBC. There's EBC. Okay. Immediately we see that the heights are not this. Okay, we can see a height. Do you see a height? Yes. We can have from C to AB. There you can have a height going across there. And from C to, so they actually have the same height, right? So let's take C for a vertex. So they do have the same height. The height is from C, you see that, from C this way. So that will be the height. And so that will be AB, half AB times H, and the other one is half EB times H. We can simplify again. Therefore, AB is equal to EB, and AB is, the total there is 6 plus 3, which is 9, and EB is 3, and we simplify that. 3:1. You always simplify a ratio. 3 parts is to 1. But we could also, if I look at AB, the lettering of ABC, we notice angle, the B is the same. So we can also see we have a common angle. So I could have also done it. This one we have two options. We could use the trigonometric formula for it as well. So I have half AB times BC and half EB times BC, and then we multiply by sine of B. So it's half AB times BC with sine of B, and there I have half EB times BC with sine of B. You can simplify, and we actually just end up with the product of the adjacent sides. So if I look at A, B, C, this here is 9 and this is 8, so it's 9 times 8. This adjacent here is 3 times 8, so that will be 3, and we simplify that, we get 3:1. So sometimes it's possible to, you can use either the standard area formula, or you can use the trigonometric area formula there. Let's look at another two triangles. So I want ABC. Let's see, there's ABC. In this case, we want EBF. Let's see, where's EBF? There's EBF, right? In this case here, definitely their heights are not the same. So we have a common angle. So we will, and what's the common angle? B. You can see there's B. Let's put B included. So I can easily see what my product would be. So let's say we don't even have to sub. So there's B. So I want A, B, C. So the adjacent side there is 9 with 8. So it's 9 times 8. And the adjacent side here are 3 and 1. So there I simplify that. Then I end up with 72 over 3, which is actually 24. Right? But we could also have figured it out another way. Let's look at ABC. They want ABC and EBF, right? Let's just put in our line EC there. If we look at ABC and EBC, the EBC fits into the ABC. And the EBC is 3/9 of the ABC. In other words, the ABC is 3 times EBC. Similarly, if I look at the BEF, it's 1/8 of the EBC, right? So I can write both of them in terms of EBC. ABC is 3 of those EBCs and EBF is 1/8 of the EBC. See, the EBF is a fraction of it there. The EBCs can cancel, and if we simplify that, we end up also with a 24. So there's an alternative in which to do that. Let's look at another diagram here, another example. Here we have a different diagram. We have triangle ABC, and we've got D and E points on BC, and T is a point on AC, and we also have that DA is parallel to TA with some measurements already calculated here. So let's just look at the ratio of some areas of triangles. Triangle ADC, let's just focus on ADC. Let's see where's ADC. There's this ADC, and TEC is a little triangle that's there. Okay, immediately you notice that you can even see from the lettering ADC, TEC. So C is common, right? What is C? C is not a height, C is an angle. So I'll use my trigonometric ratios to calculate this, which is half, and we take the product of there's the adjacent sides. This one is 9 and that one is 13, and the other side there is 3 and 5. So we have 9 and 13, the two adjacent sides, and 3 and 5. As usual, we can simplify by cancelling out. So we there have 117 is to 15, which can be simplified as 39 is to 5. Here we want to find the ratio of ABC. Let's look at ABC, that's the large triangle, and TEC here. Okay, so that's a different setup. Again, here we can see that angle C is common. There's no common height here. So I can again use my trigonometry. And that gives me here, I have 15 and 13 and 3 and 5. And if we cancel that out, and we simplify there, I get 198 is to 15, which is 13 is to 1. Now here we have another question which will be a little bit more challenging. So let's look at it carefully. We want TEC. So let's see, there's TEC, set up here, and I have ABD. First thing we notice, they don't have the same height, obviously. Secondly, there's none of the angles seem to be the same, so they don't have a common angle. So what do we do now? Okay, now we could let's see what we can do in this case. If I look at what we did in number B, we worked out the ratio of ABC is to TEC, and that was 13 is to 1. So I can see TEC is a fraction of ABC, and what fraction? It's 1/13, right? So I can write, so TEC is a fraction of ABC, so I can write the TEC in terms of ABC. Let's also look at ABD. ABD is a fraction of the ABC, and what fraction? That's 6 part, and the whole one is 15, so that's 6/15 of the ABC. So TEC is 1/13 of ABC, and the other one is 6 plus 6 plus 3, that's 15 area, right? So if we now do that, it's 1/13 of ABC, and the other one is 6/15 of the ABC. Obviously the ABCs cancel out, because we have tried to write TEC and ABD both in terms of ABC. And then we can simplify that, and that gives us the answer 5/26. Right? This one was a little bit of a challenge. That's why I've got a little bit of an asterisk there. I suggest you go over this one again. You see, if you have, there you have a triangle inside another one. So the one is a fraction of the other, right? In this case, you can see that the ABD is a fraction of the ABC. What fraction? You just look at there. This is going to be, they have the same height, so this is 6/15 of that. And we did work out the ratio between ABC and TEC, that's 13:1, so TEC is 1/13 of the ABC. Now let's look at the most important unit, and this is the one where you practice these concepts, the exercise worksheet. I suggest you go through the examples again, but pause and try, and then before you continue, and then you can try this exercise worksheet. There are 4 examples that questions that you can should be able to try. Look at the first one, and it's how I adapted it from a 2014 external examination paper. So there are some ratios, and then you can see there's even an area to be calculated there. But be careful that you always read your question carefully. Make sure you can see, and if you have parallel lines, maybe you can highlight. You see there FE and BC are parallel, so maybe highlight that. Here we have to prove, so we don't highlight it yet. Today we have to prove why it is parallel. Let's take a third. There's another question here. Again, there we have different diagram with some determine, and here we require reasons, and your reason normally is the lines are parallel, and you're using the midpoint, the proportionality theorem. Here's another question, number 5. Again, something else, very basic type of question there. You have to calculate some lengths, ratios, and there's some fractions, and then another ratio that you have to calculate. But I suggest you read it carefully and just apply what we've done in this particular video. Thank you very much for watching this video on proportionality. It is part 1 of 2 for Euclidean geometry for grade 12. Part 2 would be on similarity. To trust that this video has assisted you to improve your understanding of proportionality of triangles. You also recommended to view the other videos that we have made available to you. Please subscribe to our YouTube channel, YouTube GMMDC Nelson Mandela University. Thank you very much.